Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is Subarray maximums. In this question, we are given a binary string S of length n and our task is to find a permutation B consisting of integers from 1 to n which satisfies these two conditions. Now the conditions are if S of I is equal to 1, then there must exist a contiguous subarray B having length I whose maximum element is equal to I. And otherwise, if S of I is equal to 0, then there must not exist any subarray whose maximum element is I. So let us say we have something like 1, 0, 1, 0, 1. And if our permutation is something like 1, 2, 3, 4, 5, then in this permutation, over here, S of 1 is equal to 1, and we have a subarray, a contiguous subarray, whose maximum element is 1, which is just this much subarray, right? So this condition is satisfied. Over here, we have S of I equal to 0. So there must not be any subarray whose maximum element is 2, but there is. So this condition is not being satisfied this by this permutation. So this is not a valid permutation. And ultimately, we need to print a valid permutation which satisfies these two conditions for all I, right? And if no such valid permutation exists, then we need to simply print -1. So now let us just once see those sample inputs. So in the first input, we are given 1, 0, 1, and our output is 2, 3, and 1. So for S of 1, it is equal to 1, and there exists a permutation whose maximum element is 1. There exists a subarray whose maximum element is 1, right? Now the second element, S of 2, is equal to 0. So there must not exist any subarray, a contiguous subarray, whose its maximum element is 2. Now there are just these two possible subarrays of size 2, and this has a maximum element S3, and this also has a maximum element S3. So there does not exist anything, so this condition is also satisfied, right? And over here, S of 3 is equal to 1, so there must exist a subarray of size 3, whose maximum element is 3, which is true, obviously, right? So this is a valid possible answer for 0, 1, 1. There does not exist any permutation because a 1 would always appear in the answer, right? And because of that, we cannot print any permutation who will not have 1, right? So the answer is -1. For the third test case, we have 1, 0, 1, 1, and the output is 4, 1, 3, 2. For this, we have this 1. For this, we do not have any subarray with size 2. For this, we have this subarray whose maximum element is 3. And for this, we have this subarray whose maximum element is 4, right? You can just try out the last test case by yourself, and now let's just move to the solution. Now let us first of all analyze these two conditions properly. What does S of I equal to 1 or S of I equal to 0 mean? So if our S of I is equal to 1, then we want I elements, right? We want I elements such that the max of them is equal to I, right? This is our condition given to us. And because we're dealing with permutations, the maximum element will be I if and only if all of these elements are present inside any one possible subarray, right? Because like if these elements are not consecutively present, then some element I plus 1 would be present and the maximum would be I plus 1, right? So all of these I elements have to be present in any subarray so that like which are adjacent so that this condition is satisfied. And now if S of I is equal to 0, then this must not be adjacent, right? 1, 2, 3, dot, 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 I must not be adjacent. This is like just the contrapositive of our first state, right? So let's just do some dry run on some test cases. So what if our initial element is 0? The answer would be -1, obviously, right? Because 1 has to appear somewhere in the permutation. Now, what if this last element is 0? Again, the answer would be -1 because this implies that all the n elements must not have any contiguous subarray whose maximum element is n. But because it is a permutation, so if there are 5 elements, 5 would always be there in the permutation of size 5, right? So we cannot create any permutation, so the answer is -1. Now for this last test case, let's try to build one. So okay, there must be a 1 present, right? So let's just put a 1 directly. Now over here, there is a 0. So we cannot place a 2 over here, right? Because then there must be a permutation of size 2 which contains 2, like whose maximum element is 2. So let's not put anything as of now. Let's see over here. There is a 1. So at this index, we want all the elements 1, comma 2, comma 3 to be present, right? So what can we do? Can we just simply put 1, 3, and 2, like everything in the reverse order? Will it be valid? It will be, right? Because in no possible way 1 and 2 would be adjacent in such a permutation, and 1, 2, and 3 would be adjacent in size 3. Now over here there's a 4, so let's just put 4 directly. Over here, let's not put anything as of now, so 5 is in reserve. Now up till here, we just want to all the 6 elements, so let's just place 6 and 5 like this. And this is a valid possible construction, right? Let's just try another possible construction similarly. Let's say we have 1, 0, 0, 0, 1, 0, 1. Now how would we create a valid permutation? There's a 1, let's just place a 1 directly. We cannot place a 2. We cannot place a 3 either, right? Because if you place 2 and 3, then those elements will get filled. Up till here, we cannot place a 4, right? So these elements are in reserve. We are not putting them right. Now there's this 1, right? So we want all the elements from 1 to 5 to be present for this particular condition to be satisfied at this index, right? So let's just place all the elements in reverse, 5, 4, 3, and 2. Now, if you see that all the conditions are satisfied, right? There is no contiguous subarray which contains both 1 and 2, or all 1, 2, and 3, or 1, 2, 3, and 4, right? Because they're separated by this 5. So this 5 will become the maximum element if we just try to make any permutation of size 3 or size 4 or size 2. Now, okay, there's this again. So we'll put 6 in reserve. Then there is 7. So we'll put 7 and 6. And this is pretty much the whole construction. And that's pretty much the whole algorithm as well. Now the time complexity would be big O of n. We can easily implement it in big O of n. And that's pretty much the whole solution. So let's just look at the codes once. So this is the code in Python. So we'll begin by taking in the input of our test cases and running a loop. We'll take in the input of n and s. If s of 0 or the last element is 0, we'll just print -1. Otherwise, we'll just append 1 to our answer. We'll put the last element which we had not placed, right? Which had 0 or something. Now we'll just run a loop. If s of I is 0, we'll just continue. And if it is 1, we just place all the elements from L up till I plus 1, right? In the reversed order. So this will give us a list from L to I plus 1, and we'll reverse it, and we'll just append all of those elements inside our answer. And then we'll make our L equal to I plus 2. And in the end, we'll simply print our answer. And this is pretty much the whole solution in Python. The time complexity is big O of n because we're just running like the time complexity of whole of this loop would be big O of n, right? There might be a confusion that, okay, we are running 2 loops, so why isn't it quadratic? Why is it linear? So that is because overall it would be running big O of n times only, because if s of I is equal to 0, we're just simply continuing. And in this, our L is becoming equal to I plus 2. So if we just analyze it properly, you can see that it's just running big O of n times n total. Now let's see the solution in C++. So for each test case, we'll call this function solve. Inside this function, we'll take in the input of n and s. We'll check if s of 0 is 0 or s of the last element is 0. We'll print -1. We'll push back 1 inside our answer. We'll run a loop from 1 to n. If s of I is 0, we'll continue. Otherwise, we'll just append all the elements from I plus 1 to L inside our answer. And we'll increase our L by 2. And in the end, we'll simply just print our answer. Now, again, the time complexity is big O of n because we're just running these two loops. And the combined complexity of these two loops would be big O of n, right? And yeah, that's it for this video. I hope you liked it. Thanks. Bye-bye.